Hello, everyone. How are you all? Everyone doing good?
Good.
Good.
Okay, so I started grading the exams, but I'm yet not done. So, like, I have done grading the multiple choice problems, but still I'm on the way. I had like several other things, like courses, other things to grade as well. So, like, I was just busy grading all the time. So, I'm sorry I couldn't finish it until before this class. So I'm gonna finish it by tomorrow for the gradings. So, but you can look at the multiple choice problems that I have graded, but I haven't put the points, but I'm just saying correct or not. So like you can see, I marked there is correct or not in the blackboard. Okay, so I will update that one by tomorrow. It should be done. Okay, and I'm sorry for that. I'm working, and okay. So now. Did you get to see the multiple choice questions like being marked correct, right or wrong? Hello.
Where do we see that at? I don't see it.
In the Blackboard itself, you don't see it?
I don't see it either.
Oh, so like the one that you submitted, like, if you go to your,
The
uh,
PDF file.
yes, so like in the Blackboard itself, if you go and where you have submit your exam scanned PDF file, right? And then
Mm,
if you open that one, your submission, you should be able to see the submission. And then I have like just said like, correct or incorrect only. I haven't put the points yet. So, so okay. Do you see it?
Oh, I guess for me, like if you're talking, because you have to like click into the exam tab, right?
Not the exam. The title is like submit your exam scan PDF file.
I guess yeah, I don't see it on my like
I don't.
list.
I'm not seeing it either. All I have is
Oh,
exams.
interesting. So, okay. So maybe if I put the grades in there, then only it will show up. I don't know. Because I have done this like did the marking on the PDF file. So if you can open your submission, like so when you once you submit and you want to verify and then check, you will be able to. So can you share your? No, sorry, don't share your screen
Mm.
because yeah. But okay. Anyway, so I'll be working on it, and only like a few remaining now. So I'll just put everything, all the points, by today, tomorrow, and you should be able to see it tomorrow. Okay. Sorry for that because I had like two other classes and I had like several student appointments. It's killing me. Anyway, I cannot complain. Okay. So today we're gonna do some of the numeric problems, and also let's see in the syllabus what did I say today, what we're gonna cover, so that I'm not behind. Okay, extended lecture. Okay, so we're gonna do some problems, and also we will do start on like a new topic today. But let's do some like numeric problems today. Okay, what do you say? You guys
Sounds
would love to do that problem?
Sounds good.
Yeah. Okay, so now here, this one goes. Okay. I'm surrounded by all the electronic gadgets here to make this class happen. Okay, so I have this question. So like here, we have this block of a mass. Let me see all the parameters have been copied here. Not this one. I don't need this. Okay. Okay. So here I have this block of mass, 5 kilogram. It attached to a horizontal spring with a spring constant K. That is K equals, that is equals. Okay, so that means I need to edit this one. Okay, so K equals, what is equal sign? K equals 4 point, what is multiplication? 4 times 10 to the power of, you know what, sometimes I feel like writing is like much more easier than using this. Okay, I think like I think I can type as well. Yeah. Oh, nice. I can type through my computer, through my iPad. Nice. Okay. As in a figure, so like this, you don't worry about this figure. So the surface block rests on the in frictionless, right? And if the block is pulled out to pull out to xi, this is absolute. X of I equals 0. Y equals to same 0.500 meter and released. I don't know why there's extra space. And release. Find the speed of the block when it reaches the equilibrium point, and find the speed when x equals 0.0250 meter, and and repeat part A if the friction acts on the block with the coefficient mu k. Right, so this is like a mu, so which is a friction coefficient. So how do I write mu k? Mu underscore k equals 0.150. Okay, so this is the questions, and then the diagram. If you want to draw a diagram from this one, what do we have like a surface, and we have a block, right? And then this block is attached to a horizontal spring. So here's a wall, and this is attached to a spring. Okay. So now, if the spring constant here, the spring constant K equals 4.00 times 10 to the 2 Newton per meter. Okay. And the surface rests on the frictionless. So now here, the first case, in the first part, frictionless surface. And if this block, so now from this block, if this block is pulled to a distance of 0. This is xi, 0.0500 meter, right? And if it is pulled to that distance and then released, find the speed the block reaches the equilibrium point. So now, at what speed the block will go back at the equilibrium points? What is the velocity at this particular point would be, right? And also like find the speed when is this one. So how do we tackle this problem, right? So what are the problems that are given here? What are the things that are given to here, right? So we know only the spring constant, you know, this of this spring, and the mass is 5 kilogram, right? Mass of block equals 5 kilogram. Spring constant equals 4.00 times 10 to the power 2 Newton per meter. Okay, so that's my spring constant. And then we want to find the velocity, right? And the displacement, I can say displacement, all right? xi is 0.0500 meter, right? So these are the parameters that we know. From these parameters, what we need to find, what is my velocity? Velocity at equilibrium, or I can say like equilibrium, EQ, okay? What is my velocity? So how do we solve this problem? Any idea? Anyone? Can anyone think? Okay, so there's a chat. Okay, I didn't see this chat. Okay, so attendance, no, I haven't given the code yet. So anyone can think? Any idea? So any hint how to do this one? So which chapter did we cover today? No, last week. Which chapter did we cover? Work and energy. So that means this problem needs to be solved using which equations?
Would we need to use the potential energy and kinetic energy formulas?
Yes, right? So now when we pull these things, right? So we are pulling this thing, and then what did we do? So we stored some energy to this object, right? And this object will go back to this one in the expense of that stored energy. And the stored energy is called what?
Potential energy.
Potential energy. And the object that is moving that we call it's a uh, kinetic energy, right? So that means what did we learn from the kinetic work energy theorem is like what? Total energy of the system is always constant, right? Total energy of the system is a constant. We know total energy of a system is constant, right? Within the system. If we are not looking at the system like two different systems, just the one system. So system inside, within, system within, right? So now my initial kinetic energy, initial total energy, and my final total energy must be equal to each other, right? Right?
Yeah.
So that means my total energy, initial total energy must be equals to my final total energy. And what is my initial total energy? Initial total energy is half mvi square plus what is my potential energy? What will be my potential energy?
1/2 the constant K times x squared.
Yes, 1/2 k x squared. So let's say xi, right? And this must be equals to what? Half mv f squared. And now, what is my final position? Final position is something kxf squared. So what is my final position? All right? My final position will be what? X will be 0. Why? Since it is the equilibrium position, right? So because we measured our displacement with respect to what? We measured our displacement with respect to the equilibrium position, right? So now if this object goes back to the equilibrium, my final position is 0, right? So there is no any displacement, right? So there is no any potential energy stored in these conditions. Here we have all kinetic energy, pure kinetic energy. So now at this point, what did we do? We stressed the spring and then we released it, right? So that means at this point, we only have what? Potential energy, right? And then since also VF, sorry, VI equals to 0 since it is released from rest, right? Make sense? And so now what this our equation would look like, half kxi squared equals to half mvf squared. And what do we need to find? We need to find the final velocity. So that means my vf is equals to what? So what I can do, I can just say, okay, this my half cancels out, right? And then, so my vf equals what? K over m square root xi, right? And more appropriate will be to say plus minus, right? More appropriate will be said to plus and minus. Why is that? Why is that?
Are you asking why there's a plus and minus?
Yes.
Because if your value is squared, that means that along the domain you'll have a negative version of that and a positive version of it.
Yeah, right. It could have like both. If you do negative times negative, will be positive, right? And also, like another thing that you can see is like since it has a power of 2, so that means it will give us like two solution, one positive solution and one negative solution. Make sense? Because if this would have been like a cube, then we will get a 3 solution, and so on. The power determines how many solutions you're gonna get for your equation. Okay, this is simple algebra. So now, so that means, so this is equals to plus minus. What is my value of k? My value of k is 4 times 10 to the power 2. 4.00 times 10 to the power 2 Newton per meter, right? And the mass of the block is 5 kilogram. So 5 kilogram. And what is my displacement? My displacement is 0.0500 meter, right? So that means I'm going to find my final velocity, which is equals to plus and minus. So I have number here. So what do you guys get? Did you get 0.447 meter per second? So this is my velocity. Again, now here this plus minus, right? So you can say what direction. If in your drawing, if you say from left to right is a positive and right to left is a negative, then it's a negative velocity. So that means it is coming towards the spring. Okay. And now second part, this for the part A. So does it look simple, this problem? All right. So here we use what model? We use the energy model, right? And now the second is find the speed when x is equal to 0.2. Now B is find the speed when x equals to 0.0250 meter. So what is my speed? Right? So again here, what is xi? So xi is still positive. So that means we are still on the right hand side of the equilibrium position. Make sense? Right? Again, same here, energy conservation. Right? So what the energy conservation says? The potential energy and the final and the initial total energy must be equal, right? And so my initial energy is again half kxi squared. So okay, let me write it in the words. So energy. So again, initial energy is equals to final energy. right? And initial energy in this condition, what is my initial energy? The potential energy is half k xi square. And then my initial kinetic energy, vi square. What is my final? Half k xf square plus half mvf square, right? So now in this term, what we can eliminate? We can eliminate half vi square because the initial velocity is 0, right? So now in these conditions, we have xf because we still have some displacement 0.0250 meter to the right of the equilibrium, right? So now in this condition, we need to find vf. So that means how do we do this one? So like I can, in this expression, it is much more easier. So half, half, half cancels out. So you don't have to worry about that half. So that means my VF mvf square is equals k xi square minus xf square, right? So that means my VF is square root of k over m xi square minus xf square. Make sense? Again, what did we do? So this is like a mostly solving it algebraically, right? So any problems that you see. So now it is very clear expression, and now you can plug in your values very easily. So that means my VF is equals to square root of 4.00 times 10 to the power 2 Newton per meter divided by 5. Is it like a decimal places? There is a 5.00. Okay. 5.00. 5.00 kilogram. And now in these conditions, this x minus xf square will be also under the square root, right? So now in this condition, what is my xi? It is my 0.0500. Let me get curly braces minus 0.0250 meter square. Right, so that means this is meter square per second square. Yes, sorry, meter square. All right. So now, what this expression would look like? If I do the calculations, if I just look, not p square, it's v. What will be my v? Anyone? Anyone got the solution?
I think I got point, shoot, just lost it. 0.447.
0.447?
Yeah. What you got?
Not that number. Let me do this 0.025.
Oh, I think I forgot a parenthesis.
Okay, so what did you get?
And I got 0.387.
Yes, 0.387. And again, when you're writing a number, just write 0 point, okay? Just don't write decimal only. So it will be much more easier to see if there's a decimal, because if you just write 0.387, sometimes it is easy to miss, not to see this decimal and then say, oh, 387, you might get it wrong, right? So if you put a 0 point, it will make it like much more easier to understand, okay?
Mhm.
And also like for everyone, this is not only Dustin and me class, this is everyone's class, okay? So everyone needs to contribute in this interactions, okay? I want everyone's interactions. Dustin is leading you guys, that's good.
No, I'm gonna go muted the whole rest of the class.
No, don't mute it. Don't mute it. It will be like totally like silent, but I want everyone else to contribute as well. Make sense? If you guys don't do it, then I will force you guys to turn on the camera. Right? If you don't do it, I'll force you guys to do turn on the camera. And if you don't participate, I will take your attendance off. So you decide what you want to do. I'm giving you guys the freedom, so use it. So now in the part C. So in the part C, the problem is what we have in the part C. In the part C, I'm saying, so repeat the same. If a friction acts on the block with a coefficient mu k equals 0.150. If I have a friction coefficient. So what does that mean? So what kind of a force would be, what kind of a work will be here? Conservative, non-conservative?
Conservative. Conservative.
Con
Conservation.
no, conservative force or non-conservative force? That's what I'm asking. So do you guys remember from the last time? So conservative force and non-conservative force? Or do you guys need a refresher? What's the difference between conservative force and non-conservative force? Conservative energy and non-conservative energy.
Path taken versus whether or not that matters.
Okay, so why taking a path will matter? Which one is conservative and which one is non-conservative?
Uh, conservative does not matter,
Okay, why it doesn't matter?
because if you if you go a certain distance and you put force in and effort in to go that distance, and then it's going to change your values along with the rest of the equation,
Why?
because you're putting in more work for the same, or more force for the same amount of work from point A to point B.
Mm. So more appropriately will be like, so if your amount of the applied force is lost in somewhere, so like in a friction. So if there's a friction, what happens? The amount of force that you apply or the energy that you apply will be lost to overcome that friction. And then you cannot recover that one, right? So like in this example, what we have this spring and a mass, right? If there is no friction, so it will keep on oscillating infinitely, right? So that means whatever the energy I provided at the very beginning, with that energy, it will keep on oscillating. If there is no any friction, there is no any damping, so nothing, right? But now if there's a friction and if there's a damping in the spring itself and all other thing, so what happens? There will be loss of energy in overcoming those friction forces and damping forces. And those are called like non-conservative. So now what do we have here? So we have a friction coefficient, kinetic friction coefficient. Not the static, but the kinetic friction coefficient. So which is mu k equals 0.150, right? 0.150. That's my friction coefficient. Right, and by definition, so what we know, uh, uh, force, friction, what is friction force then? So why I need to get the friction force? So how, okay, so let me ask you this question. How the friction coefficient is related to energy? How friction coefficient is related to energy? Time to call names now. Lorena, how friction coefficient is related to energy? How can you relate? Because this friction coefficient is given, right? I cannot hear you. I think like no one can hear you. Are you talking? Because you're unmuted. Oh, okay. Okay. So how friction coefficient is, how can you relate? What's the relation between friction coefficient and energy? How can you come up with that one? Because that's the parameter that are given to us, right? So, and then we need to figure out, okay, so what happens if there's a friction coefficient mu k, and then what happens to our velocity? How these things affects our whole system? Okay. Mariam, could you help? Yes, how? Right, so isn't that like, if there's a block and there's a
Sorry,
like,
yes.
sorry?
Yes, he called my name.
Yeah, okay, could you please help?
Sorry, can you repeat that one more time?
The question is how the friction coefficient is related to energy.
I am not sure about that.
Okay, so yeah.
Yeah, I don't really
Okay.
know.
Okay, thank you, Corina, Derek, and Dustin. So now, okay. So now, the friction coefficient mu k, right? So what we know? So first, we know the force is, first of all, we know work is what? Is energy, right? And also what we know, work is what? Force times displacement. And there's a cos theta term. If theta is 0, then it will be force times displacement. So that means force times displacement, right? If theta is 0 degree. Now what is force? Now whatever force here we have a friction force and the displacement, right? And how do we write the friction force? So we know the friction force Fk is what? The friction coefficient times the normal, right? Normal reaction. So what is basically normal reaction? Normal reaction is mass times gravity. And so that means work, which is energy, is equals to mu k mz d, right? So that's a displacement. So that's how this work is related to this friction coefficient or the energy. So now, whatever the force that we applied or the stored energy, so that will be lost in this friction force, right? So meaning, so work of friction is equals to what? Whatever my final energy, initial energy minus the final energy, right? So work of friction. So, okay, let's go back into these notes and then I'll show you guys. Okay, so, dun, 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 dun. Yeah. So this is here what it is, right?
Could you post those on the Blackboard?
Oh, I did not. Oh,
You did
sorry.
not know.
Okay, maybe it was too late and then I forgot to do it. Okay, sorry about that. So here, right? So this is a non-conservative force, right? So that means the total final energy minus this initial energy will give me the work due to the non-conservative force. So that means I can go back here. So this conservative force is total energy final minus total initial energy, right? What is the total final energy? My total final energy is half mvf square plus half m uh, half kx f square, right? And what is my initial energy? Half m vi square plus half k xi square. right? So now in this one, again, it's so simple. And Vi is 0, right? Initial is 0. And only what we have. So now if you want to find for the equilibrium position for part A, for equilibrium position, my xf will be 0, right? So that means my work due to friction is what? Half m pf squared and minus half k xi squared, right? Make sense? And now what is the work due to friction? So work due to friction is always opposite, right? So it is negative because it's the energy lost. So mu k, right? Mass times gravity times whatever my displacement. What is my initial displacement? Xi. Half m vf square minus half k xi square. Make sense? Are you guys following here? To here?
Yes.
Okay. So that means now what do I need? I need to get my final velocity. So that means half mvf is it's all algebra here. So it looks like I'm deriving a formula, right? Rather than solving a problem. So half k xi square minus mu k mz xi, right? So now, so vf square, I can jump step, right? And then what I can do, so this is k xi square divided by m, right? Minus here 2 mu k, m will cancel out, g xi, and then everything square root. Did you guys follow here? What did I do? I did 2 steps together. Multiplied by 2 and divided by m on the both sides, right? So now plug in your values for all these expressions. So again, as you are watching me solving this problem, so I'm solving this algebraically, right? So same thing when you in your exam, in your test, in your homework, solve this algebraically, and then once you get all the number, all the parameters that is on the right hand side with the parameter that you will need to find on the left hand side. So now it will be much more easier to track anything, to follow your problems. Square, what is my xi? Initial position was what? 0.0500 meter square divided mass is 5.00 kilogram minus 2 times 0.150 times 9.8 meter per second square times xi is again 0.0500 meter, right? So everything is in square root. And once you do these calculations, okay, anyone help me with this calculation? What do you get?
I got 0.23.
Yeah, 0.23. So is it the right decimal places or like a right significant number? I think yes, right? Because what we have here, no, so this is how many significant 0.500. What's my number? 0.500. Yeah. So there's a three significant figure. There's a three significant figure three significant figure, three significant figure, three, 9.80. So this is like what I put it there. So if I put it here, because this was not given, so I can just write down 9.80. So three significant figure, and this is also three significant. This 2 is just a scalar number. It's just a number. It's not a measurements. So that means you can write down this in a three significant figure as 0.230 meter per second. Make sense? Make sense? Okay. Okay, so this does it, right? This problem. Okay. Now let's see if I can find another problem for you. I have another problem for you. And let's say this what it is. Okay, I'll just write it down. It will be much more easier to write it down for me. So a 50.0 kg circus, a acrobat drops from a height of 2.00 meters straight down onto a springboard with a force constant of 8.00 times 10 to the 3 Newton per meter, right? By what maximum distance does C compress a spring? Okay, can you guys try this one? And I'll give you guys 5 minutes. Yeah, so it's 6:43, so 5 minutes, so 6:48, 6:49. Yeah. If you are done, you can type in your answer in the chat. Check your calculation, Dustin. Uh, 0.5 only, or do you have other decimal places as well? Karina.
Is it 0.50?
What I have here is 0.560.
Oh yeah, 0.560.
Mhm.
But is it?
Yeah, that's the right answer.
Oh, okay.
So you got it. So Dustin, could you check your calculation?
Yeah, I'm redoing it right now.
Uh-huh.
I'm getting the same thing. I'm not sure where I'm going wrong.
Okay. Sean, you want to say something?
No,
Okay, Gabby. How about you, Gabby? Gabby, you're so quiet. Tiffany, you are so quiet. You got 0.245. I don't know what did I do wrong. Okay. So I'll give an opportunity for Corina to lead. Corina or Corina? How you pronounce your name? Sorry.
Yeah, Karina.
Corina. Okay.
Mhm.
So could you please lead and help the class? So it's an opportunity for you to share your experience. What?
Okay. So I don't know if. So at first I started by finding
Mm-hmm.
the energy, the joules,
Mm-hmm.
and for that I started with. Should I don't know if I should type the equation or just I did 50.0 kilograms for her weight,
Mm-hmm.
multiply that by gravity,
Mm-hmm.
9.8, and then multiply it by 2 meters.
Okay.
And then I don't know if this is the same equation, but it's the one I had in my notes. So I did plus
Uh-huh.
1/2 times 50 kilograms times 0 for the energy squared. And
The
that
blood.
brought me out to 980 joules.
So what you're trying to say here? So what did you do? Energy equals like a for okay. So you try to find the. So here we need to find the potential energy and the kinetic energy, right?
Hmm.
So okay. So energy. So there are like two energy, potential energy and sorry, kinetic energy, right? So here, if I draw a diagram, so there is a 50 kg circus or a brass drops from a height of 2 meter straight down to a springboard with a force constant this. By what maximum distance does she compress the spring, right? So if this is my springboard, right? There is a spring here onto the surface, and then the person here drops down from certain height h, which is 2 meter, right? I'm not worried about the significant figure here right now. And then we need to know how much this springboard gets compressed by what distance d, right? Right?
Yes.
Okay. So now to find that one, so you said like you did mgh, right?
Yes. MGH.
50 kilogram times 9.80 kilogram times 2 meter. That's what you did.
Mm-hmm.
And what did you get for this one?
Well, I did it as a full equation because I went with,
Okay, so what did you do? So mgh, sorry,
yes, and then I did the energy equation, the E equals V plus K.
E equals
So I did
b plus k.
um hold on, let me they're not so organized.
Okay. Okay. So Dustin, you redid it. Okay, so you got 0.5. So what did you do this time, Dustin? What different did you do?
Well, I think I did this way different than what y'all are talking about. I think when I was typing it in, I just mistyped something.
Mhm.
But I looked at the potential energy of gravity and I set that equal to the potential energy of the spring when it's compressed.
Uh-huh.
I ended up just having mgh equals 1/2 kx squared. And then I
Uh-huh.
substituted all the numbers in and got 0.495.
Uh-huh. So now, so what did you do? Okay, so as I understand, what did you do is like in a total energy, mgh equals half kx squared. That's what you did,
Yeah,
right? Because initial there's only a potential energy and then other is a kinetic energy. So whatever the potential energy that this person is dropping down, so that is being transferred to as a potential energy to the spring, right?
yeah. It
Right?
has to, right? It has to be conserved.
Right? It has to be conserved. So now to do this one, so now what is my mass? So my mass here is 50 kilogram times 9.80 meter per second squared times 2.00 meter equals half times 8.00 times 10 to the power 3 Newton per meter. And then what is my displacement here? X, right?
Yeah.
That's what I did. Okay.
And then I just did all the math and left x squared out there by itself and then started moving everything around to solve for x squared.
And so what did you get up to 3 decimal places?
I got 0.49, well, yeah, 0.50. So
0.50?
0.50.
0.500. That's what you got? Meter?
Yeah.
Okay.
So wouldn't, on the significant figures, wouldn't, because you have a decimal,
Mhm.
would the 0 at the end count as a significant figure? So you'd
Yes,
only have
this,
to do
this
0.5.
zero, this zero will count as a significant figure.
But why did you put a third 0 on the answer?
Oh, so no, okay, so that was my mistake. I didn't pay attention because
Yeah, I was wondering because you did that on the last problem too, and I was curious if
oh, okay. So did I do that?
I think it should just be 0.23. That's 3 significant
Oh,
figures.
yes. Yeah, so here's the three significant figure, right? So these are the three significant figure, three significant figure, three significant figure, three significant figure, and three significant figure, and three significant figure. And these are three significant figure.
Okay, so I thought if you had a decimal though, that you do count the 0 on the left as a significant figure. Is that not correct?
So on this one, no, this is not a significant figure. That's a placeholder.
Okay,
These zeros are a placeholder.
okay. God, that still screws me up.
But now, if you have one here, then this would be a significant figure number.
It's between. Okay.
All right. Okay. So now, so this is not correct answer.
Oh no.
Okay. So your answer would be like, so okay. what happens here is like, so this spring is compressed by a distance of d, right? And this person is like a certain height h, right? So this person goes all the way down to this distance, right? So when the springboard, so these are the jumping conditions. And now if I will draw a diagram, so but now from here, so this spring is compressed, right? From here, it went to this distance, right? So the total distance this person goes is from height h and h plus d, right? So the total distance went in there, right? What is the total distance this person jumps from? This person is all the way down here, right? So that is my total compression of my springboard.
Wait,
Right.
that would become your total height for falling, or that would be the.
So because this person is falling with certain heights from here, this person has some potential energy, right? Gravitational potential at this particular height,
Yeah.
right? So this gravitational potential at this height on the board, but again, she moved all the way down there, right? This is the total
Okay.
height she moved, right? So that
Mhm.
is her potential energy.
Okay.
And then everyone following it, this one? Corina, did you do the same way? So now if I have to write down my initial and final potential energy, so what I would write down my equation is kinetic energy plus potential energy due to gravity, right? And then potential energy, right? So like potential energy due to, I'll just write the potential energy due to gravity, right? This initial must be equals to kinetic energy. I'll just write down initial here. And then kinetic energy plus potential energy due to gravity is final, right? Okay, so let me do this one. Let me rewrite this one here nicely. So potential energy due to gravity plus potential energy of the spring plus kinetic energy, that is initial, right? So these are the energies included. Make sense? Yes, that's the initial potential energy. Okay, and what is my final potential energy? So potential energy due to gravity plus potential energy due to spring plus kinetic energy, my final kinetic energy, right? They both must be equal. So now, so that's why rather than directly writing numbers, if you break it down, so look at things. What are the things involved? So in this case, it is involved the person itself with some potential energy, and then the spring also has some potential energy. Right now, the spring has no potential energy. So initially, spring has no potential energy. Initially, at this beginning, oh my, initially, the spring potential energy is 0, the kinetic energy is 0, right? Right? And in here, so my kinetic energy, final kinetic energy, when the spring is completely compressed, my kinetic energy is 0. And also my potential energy due to gravity is also 0. Right? Make sense? Are you guys following here? All right. So now my potential energy due to gravity, up to what height did she drop? H. Okay. H plus D, that's the height, right? So that means my potential energy due to gravity is mg h plus D. Make sense? And this must be equals to what? So when this thing is completely compressed, so all this energy, whatever the height she compressed from, so that will be stored in what? In a spring as a potential energy. And then the energy for the spring is like what? Half K D square. Make sense? So in your expression, Dustin, here, so you only consider the height, this height, right? You didn't consider this height, which has been compressed, right? So in this condition, what would happen? She would have been like gone and dropped here, and then no more compressed. But now she went all the way down here to this height, D, so that's her potential energy, right? So now she is storing that amount of potential energy into this spring. Make sense?
Yeah.
So now we will try to solve for this one. Now again, it will be easier if we isolate this one D in some way, right? So mgh plus mgd equals half kd squared, right? And now you can write a very nice quadratic equation if you like. So what you can do, so d square equals 2mg. No, okay, I'll do this one. D square minus 2m, d square minus, not 2. Yes, sorry. So d square minus 2mg d over k minus 2mg h over k equals 0, right? So now this is a quadratic equation in terms of a d square, right? So that means I can again simplify the now. This is a quadratic equation. So what is my, if I compare this one, ax square plus bx plus c equals 0, right? Remember this quadratic equation? And the solution is what? X is what? B square, sorry, what's the solution? Anyone? Minus b plus minus b square minus 4ac divided by 2a, 2a, right? So this will be my solutions. Now substitute this, all these parameters to find this d, right? Or what you can do, you can make it this simple right here, and then get these numbers down, plug in this number for the simplicity, and then this equation would be more like d square minus, I have these numbers here already, 1 2 3 meter d minus 0.245 meter square equals 0. So now this is my quadratic equation. So here my a equals 1, b equals minus 0.123 meter, and then my c is equals to 0.245 meter square, right? And these are all, d square is a meter square, so meter times meter is meter square, and this is also meter square. So this equation is correct. Now when you solve these quadratic equations, so what I'm going to get, my d would be, so minus minus plus 0.123 plus minus square root b square is, again I will not worry about negative sign because it's already squared. Okay, I'll just write on meter here, square minus 4 times a is 1 times c is what, 0.245 divided by 2 times 1. So what do you get? What do you get for this one? Corina, did you do this way? Corina? Or
No,
it
I
was
didn't do it this way, so I'm doing it right now with you.
okay. 1, 2, 3 square minus 4 times 0.245, and then something is wrong here. C is negative value, sorry. This is negative. This is negative. Right, so that will be positive. So okay. How did I find wrong? Because this number, this value in my early, if C was not negative, so this would have been larger than this one. So in the square root, if this is a negative square root, that's imaginary and that's not possible. So that's why I found that that is wrong. Okay. 0.123 square minus 4, not minus, plus 4 times 0.245 equals this square root this plus 0.123 is divided by 2, and then I get 0.560 meter. So this is a positive one. And then if I do a negative, so now so there's like two values of these that you're gonna get, right? So now let's do this one. So now let me break it down into two parts. Now we need to figure out which solution to take, right? So now we're gonna get 0.123 meter divided by 2 plus minus, and whatever that number is, 0.123 plus 4 times 0.245. I missed it, square. Square plus 4 times 0.245. This square root equals 0.9976 divided by 2, right? I just rounded up this number, or I can just say 5, 6. I'm not caring about the other numbers. So now what do I get here? Divided by 2, this is like a plus minus 0.499, and then 0.123 divided by 2, so that is 0.0615, right? So we have like a two different values now. So there's a positive and negative. So now which one should we consider? Positive number or the negative number? What number should we consider? Anyone? Positive. Why positive?
Because you can't use a negative value, right?
So you can use a negative also. You can. No, distance is a scalar, but here it's not a distance, it's a displacement, right? Force times the displacement. But here we'll take the positive. Okay, let's look at our diagram here. So this is my height and it is compressed, right? I'm adding this distance d to my height. Make sense? You're following here? So when this person hits this springboard and the springboard gets compressed by this distance d, this distance d is added to this height, right? No one is following me?
Well, I am. I'm just trying to think, like, if we were to look at that on a coordinate plane and draw like a free body diagram, would we be using the x-axis as the board when it's not compressed?
Yeah. So
Well,
now,
negative
if my D would have been negative, if my
Okay.
D would have been negative, what would happen to this diagram?
If your D was negative,
Yes.
I don't know.
Then my springboard would be somewhere here, right? It will be spring would be stressed, right? So because the negative means from this point, it is moving up here. So because here, what did we do? So H plus D. Here we assumed our distance D is in this directions because my height is here, she is dropping down, and then she added another distance D to her dropping height. Makes sense?
So D would be negative, but height would not be.
So
Is that what you're
because
saying?
because this person, right? She is dropping from this height, and then she is compressing this spring, right? Further down, right? So that means our total height is adding up this distance D. So she is dropping down by this height, and then she is again compressing the springboard by distance D, right? So now this D is adding towards my total height, or it is decreasing my total height that she dropped.
Adding to it.
Adding to it. That's what we did in our expression, right? So in here, we're adding that height, right?
So it has to be positive then.
So yeah, so that's why this D here, we need to take this one positive. Because if we take positive, then we're adding our height. But if we take negative, what happens?
Oh,
If we
yeah.
take positive.
Okay.
For positive, positive D, so that will give me 0.560 meter. And negative D would give me what? If I select negative value to this one, I'm gonna get negative 0.437 meter, right? So now, does this negative value of D make sense? Down here is negative, so am I subtracting to this height or am I adding to my height? I'm adding, so that's why I need to choose this answer here. Make sense? Make sense? Okay, so yeah, this is what you need to understand conceptually to select if there are two answers and which one is the right one. So we'll take this positive value, positive value. We'll take this positive. Okay, make sense? Okay. I will give another one problem for you guys as a practice, but not today, but you can practice at home and then you can bring it up. But then I would like to do some problem of like a power. Okay. So I'm gonna write it down, or like I'm gonna copy and paste it down. Let me see which one it does better job. Okay, so okay, on a horizontal frictionless. Then where is my keyboard? Okay. Friction, frictionless surface, as in the figure. The block is pressed back against a spring uh, with a spring constant. For some reason, why it says a K equals like 5. Spring constant equals 625 Newton per meter. Compressing the spring the spring by 10 centimeter to the point A. I'm gonna post a picture for you guys. A. Then the box is released. Find the maximum distance D the block travels up the frictionless incline if theta is equals 30 degree. If theta, because I cannot write down symbol here, so I just typed it. Theta equals 30 degree. How fast the block is going when the halfway to the maximum height? Okay, so now I'm gonna let's see if I can copy this image. Okay, I'll take a picture then. So, picture go here. It is picture. The picture. And then I'll copy this picture and then I'll paste it here. And my screen share has been paused. Why? Where is my screen share? Oh, where is my screen? Where did my screen go? What? Oh, here. Yeah. So now paste. Yeah. Okay. So now this is my image. And then go here. Do it. So this is the image. Okay. So this is like another spring problem. Spring on a block. So this is like a little bit tricky, but I will come back to this one if I get time, and but this is for you guys to try as well. Okay, so now this is like again some with some height. Okay, so now the next problem, let me see. Oh, okay, this one is another with the power. Okay, and then here this is a total friction again. Let me. So what I have here, 1.00 times 10 to the 3 kg elevator car carries a maximum load of 8.00 times 10 to the 2 kg times 10 to the 2 kg, a constant friction force of 4.00 times 10 to the 3 Newton retards its motion upward. And the figure was the minimum power in kilowatt and in horsepower must the motor deliver to lift the fully loaded elevator car at constant speed of 3 meters per second. Okay, everything is here. Now I'm gonna get this diagram. With my mouse, yeah, because I'm going through between like 3 different screens, so I have to make sure. Okay, there's my screen here, and I say this one, and it. Let's say, can I copy? I don't know. Copy photo. Yes, I can. Notability. Paste. Okay, it did not do it. Let me go back then. Where did the image go? Not here. Sorry with this like technology. It's not always in the favor. Okay. I'm copying this one. And I'm pasting in this one here. Okay. Makes sense. Okay, so there's a problem here. Finally. Okay. So I have a 1000 kilogram elevator car carries a maximum load of 800 kilogram. A constant friction force of 4 times 10 to the 3 Newton retards its motion upward, as in figure 26. Right? What's the minimum power in kilowatts and in horsepower must the motor deliver to lift the fully loaded elevator car at the constant speed of 3 meter per second? So now, what do you understand from this problem? So there are like so many things, right, going on with this problem. So what did you understand? So when you're saying the car, the fully loaded elevator car at a constant speed of 3 meter per second, what does that mean? Oh, okay, sorry. My screen didn't get shared and you guys don't talk, you guys don't see. I have to figure out where's my mouse here. Right. Right. So this is what I have. So 1 times 10 to the kilogram. So what does this mean? When it's saying with a constant speed of 3 meter per second, right? What does this mean? 3 meter per second. Anyone? I didn't hear Gabby today. So Gabby, Gabby, you can type if your mic is not working. Okay, are you here? Yes, no? Okay, I'm gonna kick you out from this Zoom class, okay? Okay, okay. I need some response. Yes, no, I'm looking, whatever. Because I don't know, because your camera is off. I don't know if you are here or not. If I don't see a response, I'm gonna kick you out from the Zoom class now from anyone. If I call name and if you don't respond, I'm gonna kick you out. Okay. You can unmute yourself. Okay. And that's a requirement. Your mic and your camera needs to be working if you are taking an online distance course. So that's not a escape. That's not a like excuse. If it's not working, you should make your mic working. Go and find some working mic before coming to the class next time. Because last week also you had this excuse, and again, it's not acceptable. Okay. So now what do you understand by this? What do you understand by this? When we say a fully loaded car at a constant speed of 3 meter per second. So anyone can chime in, okay, sorry, chime in, and then participate in this one, in this discussion. So what we have here, when something is going with a constant speed, what does Newton's first law of motion say? What does the Newton first law of motion say?
An object at rest will remain at rest, and an object in motion will, with constant velocity.
Motion. Constant velocity, yeah, there you go, right? So now here in this one, it is moving with a what? Constant speed. So now in Newton's first law of motion, constant velocity are like in a rest unless acted by an external force, right? So that what does that mean? So there is no any external force. So now in these conditions, so when you have a constant speed, so in this condition also, we will not have a net force. So net force will be zero, right? In what condition net force as shown in this diagram, right? So net force will be zero. So what does that mean? My tension force, which is pulling this car up, and the weight of the person and the friction force, a weight of the person and the weight of this whole thing acting downward, and the friction force which was decelerating, which is going up, so they both must be equals to tension, right? Make sense? Are you guys following me here? Right? So what is happening here? So whatever the force, like if it is accelerating, if there was like a net force, if there's an if condition, if there was an F net force, then this would have been going upward, right? So, but here, constant speed means A is zero. So that means my net force is zero. If my net force is zero, so that means the total force, the upward and the downward force, they must be equal to each other, right? So here, my net force is zero. So that means my acceleration is zero. A is zero. Okay. So now in these conditions, so my force, the tension force is acting upward, right? So it's tension force. And what is the force that is acting downward? My friction force is always opposite to the motion, right? So my friction force is acting downward, right? And my the weight is acting downward, right? So that means my tension must be equals to, tension plus force due to gravity plus force due to friction force. So they must all add up to zero. Make sense? So they all add up to zero. So if I say this in a vector, this is a vector, this is a vector. So, or more appropriately, if I just want to say in a magnitude, this force must be equals to the force due to gravity plus friction in a magnitude, right? So that means if I subtract tension minus mg minus F must be equals to zero. Make sense? Right? So that means I know what should be the amount of force is acting along the cable. What that is basically tension, right? So that means I can calculate my tension from this expression. So tension equals what? What is your mass? So my friction force is like it said, there's a friction force is this one, 4 times 10 to the 3. And then mass is, so 800 and 1000. So that means it is like how much? 1.8 kilogram, Right? So mass is 1.00 times 10 to the 3 kilogram plus 8.00 times 10 to the 2 kilogram times 9.80 meter per second square minus 4.00 times 10 to the, what is the force? 10 to the 3 Newton, right? So this is my total tension force, right? So this is my force. And if you do these calculations, so you will get 2.16 times 10 to the power 4 Newton, right? So that is the amount of force the cable has to exert to move this elevator with a constant speed. Make sense? So now here, so this problem is work and energy. But again, what did we use? Newton's first law of motion, right? And then we calculate the force. Now we know the force, right? Now we need to find what? Power, right? Power equals to what? What is power? Yeah, the unit of power is watt. I mean to say WHAT, right? So power, right? So how we define power? So power is what? Energy per unit time, right? But now look at this expression. So what we have? So power is energy over time, but we found this force. How can we write down this force in terms of power? Okay. And another thing that given to us is the what? Constant speed velocity. We are not given time. We are not given energy, right? And also with this expression, we're able to find the force, but we didn't find the energy. So now, how do we calculate this energy, right? So now, before we go into that one, what is energy? I'm just breaking it down for you guys. Force times displacement, right? Because in these conditions, my elevator is moving in the same direction as the tension is being applied, right? So that means in this condition, my theta is what? What is my theta? The angle between the force and the displacement. What is the angle? What is the angle between the tension and the displacement? Zero, because they are moving in the same direction, right? So whatever they're in the tension and the same direction, the elevator is moving up. So that is zero. So that means my energy is what? Force times displacement, which is basically is nothing but work. Work is energy, right? So now if I will plug in this expression in here, so power is force times displacement over time. I can write down this force d over t. What is displacement over time? What is displacement over time? What we call that? Velocity. So that means this is basically power is force times velocity, right? So now if I want to write them, because they are both in a vector, I can also write down this as a dot product of F and V. So, or we can just say power is also equals to F V cos theta, right? Because here this is like F dot D, so like F cos theta. I can write down this cos theta. So this dot, so F V cos theta. So now since theta is 0 degree, my power is simply force times the velocity. I can write down. And now we just calculated this tension, right? We calculate this tension. Tension is what? This is the force acting along the cable upward, right? So that's the force acting along the cable upward direction, in the upward directions. So I'm not saying these are net force, right? So net force is 0 doesn't mean that all the forces are 0. All the forces are acting on it, but the sum of all the forces are 0. So this is the tension force which is being cancelled by force due to gravity and the friction force. So now this is my force which is acting onto the cable. So now I know this is my force. I know my velocity, which is 3 meters per second, right? So now then I can calculate my power, P, as force, we just calculated 2.16 times 10 to the power 4 Newton times, what is my velocity? 3 meter per second, right? So now this will give me what?
It will be 64974.
Okay,
Yeah.
649, right? 10 to the power
Mhm.
4 watt, right? So this is my watt. And it said in the horsepower as well. So like, so these
We
like
have
two bigger
Do we have
numbers.
to convert it?
Yeah, but like in generally, if I have to ask you, I will not do that one.
Okay.
Or I'll give you the conversion. So how many kilowatt equals to how much horsepower? Okay. So generally this now write down this in terms of a kilowatt, right? So this is like a 64.9 times 10 to the power 3 watt, which is basically 64.8 kilowatt. Okay. Make sense? So do you see? So this is how you will formulate the problem, right? So this is like a force. So again, so just asking this simple problem, you see there's an application of Newton's first law, Newton's second law, the work, energy, and the power. And then also we got like a new definition of the power, which is power is basically force times the velocity. So now if you're driving a car and if you're towing a car with a cable and you're going with certain speed, V, then you can calculate what is the power that is needed to tow a car. Make sense? Okay, so this is force times velocity. Now, so that means now I will give you guys, okay, so it's like almost like a 7:40. We will come back in 10 minutes and then we'll do one more problem and then we'll move into the next topic. Maybe 2 more problems and then we'll go to the next chapter. Sounds good? Okay. Okay, so Dustin, unmute yourself. Okay.
All right.
All right. Okay, hello everyone. Welcome back again.
Hello.
Okay, hello. Okay. So there's a problem here. So killer whales are known to reach 32 feet in length and have a mass of over 8,000 kilograms. They are also very quick and able to accelerate up to 30 miles per hour in a matter of seconds. Disregarding the considerable drag force of water, calculate the average power a killer whale named Shamu with mass. Mhm. Killer whale name. Name Samu with mass 8,000 kilogram would need to generate to reach a speed of 12 meter per second in 6 seconds. So what's the power we need? So what do we need to do to solve this problem? So what we need to do is that we need to find how much the energy. So again, what's the power? Power is energy per unit time. And we have known, we are given the time is 6 seconds. All right. And now we need to find the energy. So again, what we know the definition of energy? Anyone? So from work energy theorem, what do we know?
The capacity to do work.
Capacity to do work, that's the definition, right? So in mathematically, how do we write that expression? So from work energy theorem. Work is also equals to what? Change in kinetic energy. Do you remember this? So if I will go here and then work energy theorem, right? So this is the work energy theorem. So where the net work done is what? The difference in kinetic energy, initial and the final kinetic energy. Do you remember? We did this area under the curve, rectangle, and then we figure out this energy work done is what? Changing the kinetic energy, right? So that means my work is half k square, and it said like, what do we need to do? Calculate the power needed for the killer whale named Shamu with mass 8,000 kilogram would need to generate to reach a speed of 12 meter per second in 6 seconds. So what is my initial velocity? So based on this one, what is my initial velocity?
0.
0 meter per second. And what was my final velocity? So I need to go 12 meter per second, right? So now work done is what? That energy is change in kinetic energy. So half m Vf square minus half m Vi square. Now my initial velocity is 0, so I don't have to worry about this one. So then I can easily calculate my energy, right? So which is equals to half times 8 times 0, 0 times 10 to the 3 times final velocity is 12.0 meter per second whole square. That's the good thing about this electronics. So I can just drag and make space, right? So now this is equals to minus 0. So that means my work done is equals to, so this will give me 5.76 times 10 to the 5 joule. That's my work. And what's my power now? In this case, I don't need to do force times velocity because I know what's my power. Energy is given. Energy not given, we calculated, right? So energy. And what is my time? my delta t, which is 6 seconds, so 5.76 10 to the power 5 joule over time is 6.00 seconds. So if you calculate, this is 9.60 times 10 to the 4 watt. Okay, so this W is different than the other W. This is watt unit. Make sense? It's that simple, this problem. Let's see.
So I have a question. Why wouldn't it be in joules? Because isn't watts a rate of joule transfer over time?
Joule per second. You can also write down this one, or you can just write down 9.60 times 10 to the power 4 joule per second. You can write down. There's nothing wrong with that.
Okay.
So, but like generally, so like everyone wants to have like a minimum work as to do. So you have to type J and then slash and S rather than just type W. It's much easier, right?
Okay.
It's a derived unit. Okay. So this is one problem, and let me see the average power. What it is? The speedboat needs to rest. Okay. 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 So I have another problem here. One more problem. And let me go back to my keyboard and let me type here. What average power would a 1.00 times 10 to the 3 kg speed boat need to go from race to 20.0 meter per second in 5.00 second, assuming the water exerts a constant drag uh, drag force of magnitude f underscore d equals 5.00 times 10 to the 2 Newton, and the acceleration is constant. We find an expression for the instantaneous power in terms of the drag force F d, the mass m, acceleration a, and time t. So so there are two parts. First a and then this b. Okay. So in these conditions, now we need to find what the average power would be. Our speedboat needs to go from rest to this in 5 seconds. In the water, is a constant drag force of magnitude this, and the acceleration is constant. So can you go ahead and try this problem and then see what you get? So how we solve this problem? It's a tricky one, right? Okay. Rather than that, I'll just go ahead and solve this problem for you guys. Unless you want to do it, try. Do you guys want to try? What? Okay, go ahead and try. So you got a net force. Okay, and also way to go from there. Okay. So how about you got 40 kilowatts? So you're close, Mariam. Okay, nice. So what I have here is 45 kilowatts. So you are 40 kilowatts. Okay, how did you do it? You're good. How did you get that number? Can you explain what you're trying to find first? You can unmute and talk. That will be much more easier to do. Okay. So Dustin and Lorena, so did you guys get anything?
I'm still in the middle of it.
Okay. Average 45 kilowatt. Nice. Okay. Yes, I'm impressed. So, Derek, you said like you got a force, right? Net force. What do you mean by net force? So, the force, the power. Go ahead.
So I calculated like the acceleration, and then like I got the net force of the boat to be 4,000, but then you have to calculate, or I guess account for the drag.
Mm.
So then I added that to the 4,000 to get,
So you calculate acceleration.
yeah,
What did you get for your acceleration?
4 meters per second squared.
Yeah, so that's very right. That's correct, right? And then from this acceleration, so remember work done by the drag force. So we are given the drag force, right? Right.
Mhm.
So that means to calculate the work done by the drag force, the force is already given. Only thing what we need to find based on the definition of work. What is the definition of work? How you do mathematically when you calculate the work? How you calculate work?
Oh.
Force times displacement, right?
Yeah.
So now you have a drag force. Now you need to know how far it will go if you are going with the speed of 20, because your speed is already given, right? Your speed boat needs to go from rest uh, at the speed of 20 meter per second in 5 seconds. So that means the time is 5 seconds, the speed is 20 meter per second. So that means in 5 seconds, how much distance do you go? If you know that, and you have a drag force is same as like what, a friction force, right? And then friction force, work done by the friction force depends on the what? Path it has taken. All right. Now to find the work done by the friction force, what you need to do? Friction force times the path length, right? Is that how you did, Jacob and Mariam? Is that how you did, Jacob?
Sorry, I
Derek did.
was trying to do on the part two. It's like, I'm sorry. What was the question?
Okay. So how did you do it? You found the acceleration, and after acceleration, what did you find?
I found the average power, which is
How
the
did you? Okay.
total
How did you?
times velocity over 2.
Force times velocity over 2. Okay, that's how you did.
Yeah.
Hmm.
And then I found
Which
the
force? Which force did you use?
for 4.50 times 10 over 3 Newton
4.50.
times the 10 over 3 Newton times 20 point 20.0.
4 points Newton force. What is 4 point Newton?
And I found the average velocity.
Okay, what did you find the average velocity?
Wait.
Okay. Yeah, can you because you got like a correct answer, but I'm just like, can you? Is it possible that you can annotate in my screen?
Yeah.
Okay, go ahead and annotate and then do it.
Okay. I write down mass equal 1.00 times 10 to 3 kilogram.
Uh-huh. Okay.
Initial velocity u equals 0
Uh-huh.
per second. And the
Uh-huh.
final velocity is 20.0 meter per second.
Okay.
Time equals 5.00 second. And drag force
Mhm.
is 5.00 times 10 over 2 Newton.
Okay.
And And the first calculate the acceleration if velocity minus initial velocity over time, which is 20.0 meter per second minus 0 over 5.00 second. It's equal to 4.00 meter per second squared.
Mm-hmm.
And then I found the force needed to acceleration, and mass times acceleration.
Mm-hmm. You did
It's
force
equal to 4.00 times 10 to 3, 10 over 3 Newton.
So you did like 1.00 times 10 to the 3 times acceleration is 4.00 meter per second square. You said like this is force that it is pulling is like 4.00
4.00
10 to the
times
3 Newton,
Newton.
right?
Yes.
That's you did. And then you have to find power. You did
Right.
force as velocity.
Acceleration plus 5.00 times 10 over 2 Newton.
Okay. I didn't get it. Sorry.
Sorry.
Okay.
And the total force, I found the total force.
What is the total force? What is your total force?
It's equal to acceleration plus times over times, I'm sorry. It's drag force from the water that is equal to is like 5.00 times 10 over 2 Newton.
So like total force is force plus drag force. That's what you did.
So total force equal acceleration plus the drag force from water.
Acceleration, mass times acceleration, or like what?
5.00 times 10 over 2 Newton.
So this is like what did you put? So like this is like this
Drag
mass times acceleration is this, right?
Yeah.
That's what it did. So 4.00 times 10 to the 3 plus 5.00 times 10 to the 2 Newton. That's
Yeah.
what it did. And then
Yes.
the total force is
4.50 times 10 over 4, 10 to the 4 what?
10 to the 4. Hmm. Hmm. So then you use this
Just
force.
if they divided by 10, 10, 10 to the 3, which is equal to 45.0 kilowatt.
So like, okay, sorry, I didn't get it. Like what you're trying to say, like what you're trying to do here. I didn't get it. What exactly? So you said you found the velocity. Okay, so like
10 to the 4.
okay, so like okay, tell me what you do. So like, so you know. So okay, let's do this. We know the power
Yes.
is work over time, and also power is force times velocity, right?
Yeah.
Which one did you use to calculate your power? And Derek, so you too. Which one did you use?
The right side.
So this one.
Yes.
Okay, so I said this is equation number 1. This is now equation number 2. Right?
Wait,
You
why
what?
did I divide it 2?
No. So equation 2. I'm writing equation 2.
Yeah, I divided force times velocity over 2.
First time velocity divided by 2
Yeah.
to get the average velocity.
Yeah. Wait,
That's what it did.
yeah.
Okay. So and your force was like according to you, so your force was 4.5 times 10 to the 3 times 5 divided by 2. And then so let's see what you get. 4.5 times 5 divided by 2. I get different number. So 4.5 times 5
What did you get?
divided by 2, 11.25, right?
Mm,
So this is what you did, right? That's what you're saying, right?
Yeah.
This is what you did, right? So that's what you're saying. And but with this one, I'll get 4.5 E to the 3 times 5 divided by 2. I'll get 11.250 watt. This is what I get.
Okay.
That's not what I get. That's not the right answer. So
I'm
Derek,
just
Dustin, how
looking
did?
at the paper that what I missed to tell you. It's like,
Okay, let me do this, right? Okay,
yes.
okay, let me do this. So we have a mass. I'll just write down one after another. This is my mass, right? And then my velocity, my final velocity is 20.0 meter per second, and my time is 5 seconds, and my drag force is 5 times 5.00 times 10 to the 2 Newton, right? And A is constant, right? So, and then what you need to find? I need to find power, right? Make sense? So power, the boat engine needs to have, the boat needs to have, right? The speedboat needs to have a power. What power this my boat needs to have, right? And from definition, power is work over time or force times velocity, right? Right? There are two different definition.
Yes.
Make sense? So now to find the force, right? So we have a drag force, as you said. Why am I okay recording? So there is a drag force, right? So whatever the energy the boat is supplying, what happened to my? Sorry, my this. Okay. So whatever the energy that is supplying, so some of the energy will be used up to overcome this drag force, right? So that means my engine needs to have a, come on. What is, what happened? Why is not responding? Okay. So my work due to engine needs to what? Needs to provide the energy due to drag plus what? Plus I need to have a kinetic energy, right? So my engine needs to provide this drag energy plus the energy due to final velocity Vf, right? Make sense?
Yeah.
Make sense? So now, so this is what I need. Why am I, it's not working. Okay. So now this is my work. And so this work energy, whatever the supplied energy by the engine will be used to get my speed, which is the velocity, kinetic energy. And that is the supplied energy is not only used up to get the velocity, but is also used up to overcome this drag force, drag energy, right? And then we know the drag energy, sorry, we know the drag energy is what? Drag force times the what? Displacement, right? Make sense? Make sense? So now this drag force depends upon my path. In this drag force is not force times velocity, is like a force times the displacement, right? So that's my energy. Simple definition, force times displacement. Make sense? Right? But this drag energy is that is what is being lost. So now I need to know, but do I know delta x? Do I know delta x? We don't know, right? We don't know because the boat might be going like a curvy path or it might be going straight. It's a different thing, right? So, but now here we don't know. Suppose it's going straight, but still I don't know what is my delta x, right? Do I know?
No, but you can figure it out.
Yeah. So now how do we calculate? So now it comes down to the problem of like a one-dimensional kinematics, right? Now the problem is now we need to find delta x, right? So now how do you calculate delta x? So we know from our definition, v square equals vf square equals vi square plus 2a delta x. Right? That's what we know from our kinematics, right? 2a delta x. And what is my initial velocity in these conditions? Again, initial velocity is nothing but 0, right? So that means this expression is nothing but simply vf square is equals to 2a delta x, right? So now because I know my final velocity, but I don't know my acceleration. Now my question is, what is my acceleration, right? Now, if I know my acceleration, then I can calculate my delta x easily, right? If I calculate my delta x, then I can calculate my drag force. Make sense? Right? So that means now, again, what equation do I have? Final velocity is equals to initial velocity plus acceleration times time. Do we have time? Is it given? And yes, it is given. So time is 5 seconds. And then again, it's very simple expression is 0. So that means from this my Vf is 20 meter per second equals 0 plus a times 5 seconds. So what is my a is 4.0 meter per second square. Right? Make sense? So now I got my acceleration. So now if I get my acceleration, now if I substitute this in this one here, right? So my delta x in that condition would be Vf square over 2 times a. So that means my delta x is, what is my final velocity? 20.0 meter per second whole square divided by 2 times 4.0 meter per second square. So what that delta x will give you? What the delta x will be in these conditions? So what is 400.0 meter square second square divided by 2 times 4.0 meter per second square, right? That will give me my delta x is 50.0 meter. Make sense? Because this 150. Make sense? So my delta x is here. So that means my work done due to drag force Ft times delta x. So W drag, what is my force due to drag? 5.00 times 10 to the power 2 Newton times 50.0 meter. So my drag energy is what? 2.50 times 10 to the power 4 joule, right? Right. So this drag, again here I didn't write the negative sign because the way I wrote my equation here, so I'm already considering that one negative is already being added. Okay. So that means to calculate the energy required for the engine, again I heard this. Okay, energy required by this engine is the energy lost in the drag force plus the kinetic energy gain, right? Work due to engine is equals to W drag plus half mv f square. So W drag is 2.50 times 10 to the power 4 joule plus half. What's the mass? Is like 100 times 10 to the 3 kilogram times 20 meter per second square, right? And this will give you what? Your engine 2.25 times 10 to the power 5 joule. Make sense? So that means my power is work due to engine divided by time 2.25 times 10 to the power 5 divided by 5 seconds, right? And this joule, so now this is 4.50 times 10 to the power 4 watt. Right. Make sense? Average power. Okay, so this is this one. Do you have any questions anywhere?
Do we still have to do the instantaneous or
Oh,
leave that?
instantaneous expression. So
Yeah.
instantaneous, right? So at any point, right? What is the force at that at any time, right? So again, so part B for the instantaneous force. So whatever the acceleration at that particular time is what? Force due to engine minus drag force, right? At any time, the net force is what? Force due to the engine times the drag force. And so that means force due to engine is mass times acceleration plus drag force, right? So what is power? At any time, the force at that particular time times the speed at that particular time, right? And force at that particular time is what? Mass times acceleration times drag force times the velocity, right? And now, so this is the velocity, and the problem we are given like constant acceleration. We can also write down this velocity as what? What we can write down? Vf is equals to Vi plus At. So Vi is 0, so Vf is At. So that means I can write down this as At. right? So that means this is m a square plus fda times t, right? Make sense? So this is my power at any time. At that particular time, what is my acceleration? Based on that acceleration, that will be my power at that particular instant of time. Okay. Okay. So this is what it is. And so I have for you guys to do this one, try yourself. So this one problem yourself uh, as a practice. And then if you cannot, we will do in the next class. And now we will switch gear to our next topic. Are you guys ready for the next topic? Yeah, good. So now the next topic is the momentum. The next topic is the momentum. So why momentum? Right? So let's see in the blackboard. Why do we need this momentum? Until now, we studied about like all this kinematic motion and then uh, projectile motion and then force, and then we read about the energy. But now the next topic is the momentum. What's the purpose, right? So again, as I mentioned earlier, so every time we are making a new model, every time we are working on a new model to solve a new type of problem. So with the energy, as you saw, so we can calculate the velocity, right, in a system, and then within the system, right, the velocity of of an object within the system by using the conservation of energy. But now, if you have situations uh, like if you are shooting an bow and arrow, or like you are shooting a rifle, right? So there's a recoil energy and there's a like a recoil velocity that you go back, right? And now if you are given the mass, right? So like now it becomes a two-body system. Until now it's like all like one body system. Now when it becomes like a two-body system, when the bullet is being fired from the rifle muzzle, so now the bullet leaves the original mass, right? And that small mass is moving with a certain velocity. And then because now to conserve that one, the other one needs to move backward. Now with the conservation of energy, can we solve that kind of a problem? Can we solve that kind of a problem? And the answer to that one is no. We cannot solve that problem uh, using conservation of energy. Just a second, let's see if I can find it here in the book. Momentum, 14 to 15. Okay, so it doesn't say here in this book. Okay, anyway, so that's fine, right? So we cannot solve that kind of a problem using the energy conservation. So like now we need another type of example. So where we can find the speed of particles. So meaning here, okay, now here, linear momentum and collision. All right. So now to this one. So like suppose like there's an archer is pulling and then trying to throw this arrow, right? And then once this the arrow is being delivered, right? This here, archer, if the archer is sitting on, standing on top of like ice, this ice, meaning there is no friction. So this archer will go with some velocity, VA. So this person will move back automatically with some velocity, VP person, right? So this person will move with some velocity. Earlier, they were all one system. This the arrow, the person, this bow, everything was just one single person. But now here, it's not a one single person. It's like now two different system here, right? So now when this thing is separates out from this one, now because of that, so this person moves backward. So and an energy model cannot solve this kind of a problem. To solve this kind of a problem, now it comes a different topic called momentum, conservation of momentum, linear momentum. And this type of linear momentum is also can be used to understand when the new baby is born, we ask not to shake a baby. Do you know that? A baby should not be sick, otherwise there will be a what? A brain injury, right? Do you guys know?
Yeah, I actually had a whole seminar in high school where they came through and they gave everybody T-shirts with baby pictures on them, and they said never ever shake a baby on them.
Why? Why is that? What happens?
Well, I mean, it just seems like violent and crazy to shake a baby first and foremost.
Okay, there's a one foremost. Okay, and what's the another one reason?
Well, I mean, their brain is going to smack against its skull
Mm-hmm.
and give them brain damage.
So brain damage, right? So I don't know what's this second baby syndrome. Okay,
Yeah.
so yeah. So because the baby was second, right? So like this diagram here, it shows here. So our human brain has a little bit of a space here. There's like little fluid. Our brain is like nothing but what? A fat and water, right? And then here, so there is like this cerebral fluid, whatever that is, that covers our brain and then protects for everything. But now when you do vigorously move a baby, so according to Newton's first law of motion, what happens? Everything in a rest wants to stay in a rest, or if it's in a motion, it wants to stay in a motion. But now, so since this brain is in a rest, so there's a space between the skull and the brain with some fluid. Now, all of a sudden, when you move the body, the brain will left behind, and then the skull will move forward, right? And what happens? The brain will smash on the back of the head, right? So there's brain injury. And now again, you move back and forth. Now the brain already started moving forward because now it started smack. Now again, if you move backward again, all of a sudden, your skull moves backward, but your brain still wants to continue move forward. And then this brain gets smacked on the frontal side of the skull, right? And if you do this vigorous thing continuously, what happens? The front and the back, they will continuously hit each other, and what happens? There's a brain damage. So it's the same reason. So when you shake your head really, really hard, you you turn your head really, really hard, so you get like kind of like a dizziness and all those things. Why? Your brain is like going all around, right? So that's why the heavy metal rock head banging, not a very good idea. And also like one of the reason, like, the in a football game, so there's like it's a more injury prone and sports, because when you do tackle, all of a sudden you are going with a very high speed, and all of a sudden you've been tackled by a person, right? Or the other person. No matter how much like foam you use in your head, yes, the external damage, there's no external damage, but your brain, again, your brain has this space, right? So they are not like firmly tied to an object like a skull, right? You stop, right? But now, when there's like a space in your brain, so all of a sudden when you get tackled, even though outside there you have like a lot of cushioning, your brain might get stop really fast, and then it might get a hit. Again, this cushioning will help. So we'll talk about that, how this cushioning will help for not getting injury. But again, there's a chances of getting an injury, high impact injury. And this kind of a model can be explained. So why it is so risky and why it is so dangerous to do that one. So we'll talk about that in this chapter. Okay. So a little bit of biology, the applications, all right. So now whenever we talk about the momentum, so momentum is nothing, but it's just mass times the velocity. Very simple expression. And it's defined by an expression P, and this P momentum is nothing but mass times velocity. And now if you see here, the mass is a scalar quantity and V is a vector quantity. So this momentum P is also a vector quantity, because if you multiply a vector with a scalar, it is still a vector, right? So M is a scalar quantity. So that means my momentum is also a vector quantity. So that means my momentum has a direction. The same way the velocity has a direction, then my momentum also has a direction. It's not like an energy. Okay, so that's why shaking back and forth is really, really, really bad. All right, so because like a brain keeps on moving forward, and then all of a sudden you move backward. So what happens? There's like a what do you call, like a borrowed force kind of thing, right? And then it hits each other, collide. And now, if there is a change in momentum, if we do, there is a change in momentum. So change in momentum can happen by two different conditions. Either we change the mass or we change the velocity, right? Changing the mass in a simple problem, like an object moving, right? Or like a person walking. So that is not very feasible. But generally it's like, okay, if we change the momentum, we say the change in momentum is like due to change in velocity. But this is not always true. Change in momentum is not always due to change in velocity. One big example, everyone knows this one, but you might not have like noticed. If you're driving a car and you're changing your speed, right? Is that the change in momentum is coming solely due to the change in velocity? Anyone? If you are driving a car and then you gain some speed, does that mean that change in velocity or change in momentum is coming solely due to change in velocity? Okay, if you say that. So now, if you are planning to go into the space, there's a rocket, right? And this, when the rocket is propelling up and there is a change in momentum, now that change in momentum is solely coming because of the speed of the rocket, the change in momentum of the rocket. This is another one. So from car, I move to rocket.
What are you asking? I'm sorry, I'm not really understanding.
Okay. So when the rocket is like flying up in the space, right?
Mhm.
So now there is a change in momentum, right? So in
Yeah.
that condition, the change in momentum is it coming solely from the change in velocity? That's my question.
I feel
Is
like it
my
would have to be because there's no change in mass happening, right?
Are you sure?
Mass is weight has to do with gravity.
No, it's a mass. Mass is a scalar quantity. It has nothing to do with the gravity.
Oh yeah, you're right. That's weight. Sorry.
Uh-huh. So now, okay. So I think like so we all travel in airlines, right? We
Yeah.
all travel in airlines. And then we are asked that we can only carry one luggage of certain weight. So if you're traveling international, depending on the airlines, they will say like your baggage limit is like a 55 pound, or like, if you're going through Qatar Airways, so then your baggage limit is like 2 baggage per person, 55 times 2, right? So that's your baggage like a limit. Why that baggage limit is there?
I think I thought it was because of like fuel consumption.
Fuel consumptions, right? Okay, so okay, for somehow I made like a very efficient like a airplane, right? And like so, if my total airplane can fly, the total weight of the plane can fly is like a 300 passengers. Suppose 300 passengers, and then including the passenger and everything with the plane and everything, suppose say it's like a how many say like 500,000 ton. Okay, suppose a 500,000 ton. So
Okay.
now, if the plane can fly 500,000 ton, can I put 500,000 ton of passenger and like a luggage in there?
I mean, if that's like the total capacity of the plane loaded, yeah, what?
Totally loaded with the plane weight and everything. If 500,000 ton, can I put like 500,000 ton of people there?
Are you considering the people part of the load? Or are you asking if we can add another 500 tons worth of
No.
people?
So people also as a load, like total capacity with the airplane itself and the people in and the luggage, so total weight, total
Yeah.
including airplanes. Can I
Okay.
put like 500,000 ton of people there?
I don't see why not.
Okay. So then, where are you gonna put the fuel then?
Well, that's what I was considering part of the total load.
No, I said like all the engines and everything, right? And the total, including the engines, whatever. So 500,000 ton, the airplane can fly. So that means, can I put 500,000 ton of people there?
Yeah, I don't
Definitely
know.
not.
I don't know. I don't know what I'm not understanding, I don't think.
Okay. So okay, let me draw this diagram. This is my, oh no, such a bad. Okay, so like undo. Okay, so this is my plane, right? Right? Everything including this plane can fly a total weight. Everything, the plane weight itself. Okay. Total mass, I would say. Okay, not the weight. 500,000 ton. Okay. Now, can I put 500,000 ton of load in this plane to fly? Can I put
Yeah, it can fly with that total weight.
500,000 of like load in the plane? So
Oh,
everything including, can I put this 500,000 ton in this plane? So this plane is that fly, right? And then I have this cargo with 500,000 ton. Can I put this inside this plane, this 500,000 ton of load? Can I put this
no, because you're saying including the plane, it can fly at 500,000, right?
Yeah.
So you can't
Yes.
add 500,000 to the plane's load.
Yeah. So no matter what, I cannot have 500,000 because the everything including 500,000. Now here, I'm adding like, so what weight do I need to subtract? So I need to subtract the weight of the plane. If the plane is 500,000, if the plane is suppose a 300,000 ton, then how much room I have to put in this plane? How much load I can put?
200,000.
200,000, right? Can I put all 200,000 load in this plane now? Can I?
I think so.
Okay. So then if I put all these 200,000 loads in this plane, then this is like a metal engine. This is a metal like a box. And then this 200,000, this is 5,000.
Okay.
To fly, what you need? Can plane just fly?
No, you gotta have fuel.
You need a fuel. So do I need a room for fuel?
Yeah.
So that means can I put 200,000 tons?
No.
No. So that means maybe like another like 50,000 ton of fuel is required. Like this is like a fuel, right?
Hmm.
And then I have like a load of 150,000 ton, right? So I can put in the plane, right? Because 50,000 is a fuel, right?
Hmm.
Right. So now we said that 50,000 is a fuel. So now as this plane is flying in the air, mid of the air, with some velocity, will this 50,000 ton fuel or will always remain 50,000 ton of fuel in the air?
No, it's constantly being depleted.
Is being depleted. So now what is happening to the mass?
It's changing. It's getting lighter.
Mass is changing, right? So now here, so there's a velocity and you're getting an acceleration. Is this change in acceleration is not only just because of what? The velocity, but also there is a change in mass.
Okay.
So this change in, so now this momentum change is not only due to the change in velocity, but change in mass as well, right? So now this change in momentum per unit time is known as a force. Now, if somehow that you are running yourself, even when you are running, you are sweating, right? You are losing the mass, but that loss in mass is like a lot small compared to the jet engine exhausting the fuel, right? So
Hmm.
in that condition, we say considerably this mass is like a constant. And then what do you see? This say rate of changes momentum is like what? What this quantity? A is so acceleration is change in velocity over change in time, right? So what does that give me? So this rate of changes momentum, change in momentum over change in time is what? Mass times acceleration. So what does that give me? A new definition of force, which force is rate of change of momentum, right? So now here is delta P over delta T. So what is delta P? This is change in momentum, right? So now this change in momentum can happen either by change in velocity or by change in mass. So that's why this is much more appropriate definition of force than simply saying mass times acceleration. With this expression, you are also taking care of the situation where the mass might be changing, right? Like an airplane, like a rocket, like a car, a gasoline car. As it is learning, it burns out the gas, right? And it is losing its weight, right? When your car is like fully tank full of gas, so 15 gallon of gas weight is there. But as you are driving, it gets like a weight small, gets the mass gets depleted as the fuel keeps on burning, right? So that means your car will be efficient near where the fuel is almost like empty because now your car doesn't have to drag that much of weight, the fuel weight itself. Make sense?
Yeah.
Right? So that's why this is the much more appropriate definition, which will taking care of the change in momentum, which is like a change in mass and also change in the velocity. Make sense? And this is a new definition of Newton's second law of motion. Make sense? So, and then this momentum also follows the same rule as the rule of vector additions, right? So this momentum, if there are like a several momentum, P1, P2, P3, and Pn momentums, all this total momentum of this, the final momentum of the system is what? The vector sum of all this momentum of this nth particle. So like if a system has like n different particles, and each n different particles has like individual momentum, P1, P2, P3, and so on, then the total momentum of the system of n particles is the vector sum of all this momentum. Make sense? Is the vector sum of all these moments. It is not an algebraic sum, it's a vector sum. Remember in my problem here, earlier I did this expression here, here. So this expression here. So here I didn't mention like any negative sign here, but like here in the magnitude, so but this is what? Negative sign here. Right? So this is a vector sum. It's a positive negative. So now here the direction was not defined. So this direction was hidden in the vector sign itself. So all this vector sum or this momentum is the same thing. P1, P2, P3, this is not the algebraic sum, but these are the vector sum. Make sense? And the same thing, I can write down this term as like what? M2, M1 V1, M2 V2, plus so on and so forth, up to Mn Vm. Right? So again, same thing, components, like as you said, x component of the velocity, y component of the velocity, and z component of the velocity. So same thing for the momentum also. It's like x momentum is mass times the x component of the velocity. Again, this mass is a scalar quantity, so it's nothing. But only thing is like momentum is nothing but a velocity multiplied by mass. Everything that we did for mass is same thing for the momentum. Okay. And what's the difference between the momentum and the kinetic energy? Right? If two objects have the same momentum but different mass, which statement about them is correct here? If two objects have the same momentum but different mass, which statement about them is correct? The one with the smaller mass has more kinetic energy. Both objects have the same kinetic energy. One with the greater mass has more kinetic energy. This is for you guys to answer. Two objects have the same momentum but different masses. Which statement about them is correct? The one with the smaller mass has more kinetic energy. Both objects have the same kinetic energy. One with the greater mass has more kinetic energy.
It would be C, right?
It would be C. Okay. So why are you saying it will be C?
Because kinetic energy is half of the mass times the velocity squared. So the higher mass would give you a bigger number.
Okay, so that's your answer, Derek. And Corina, you also said this is C. Is that the same reasoning?
I think it's A.
You think it's A. So why
Yeah,
do
I
you think?
was using.
Okay. So how about Mariam, Mary, Lorena, Sean, Jacob, and Gabby?
Is momentum the product of yeah, is the momentum the product of the kinetic energy, or is it the other way around?
Didn't we? I
I-
gave a whole lecture just.
Yeah. Well, that's why I'm like
What is
confused by it.
momentum? What did we just say? Momentum is what? Someone helps on. You might be sleeping. It's already night. 9 o'clock. Is your night
I think I just kind of
dozed off?
yeah, I don't know.
Okay. So momentum is mass times velocity. Thank you, Lorena. Okay. So momentum is mass times velocity. Now here, two objects have the same momentum but different masses. which statement is true? So like Jacob and Dustin is saying A and Mariam said yes. What does that yes means? I don't know. Okay, Mariam is saying A. And how about Mary and Lorena? Yeah, Lorena, what is your choice?
I want to say A, but I'm not fully sure.
Okay,
Yeah,
you want to
I
say
think
A.
I think it's A if it's
Okay, you think
higher
A. A
momentum,
with
right?
smaller mass. Okay, so can anyone tell me why? So like, okay, Lorena, so you are the last one to answer your type your answer. So why do you think like it's A? Okay. You're typing or not? I don't know. Okay. What is mass times velocity is momentum, right? Yes. Right. So now the question was uh, same momentum but different masses, right? So now let's see. So now if I say M1 V1 and another one is M2 V2. Okay. And we said these two momentums are equal. And let's say here M2 is greater than M1. Right? If M2 is greater than M1, what will happen to what is the relation between V1 and V2? So now if I say M1 V1 equals to M2 V2, so V1 over V2 is equals M2 over M1. So that means V1 over V2 is greater than 1, right? So V1 is greater than 1, so that means V1 is greater than V2. What is V1? So V1 is the velocity of a smaller mass. Now look at the definition of kinetic energy. Half mv squared. So here, mass is a single unit, V is a double unit, right? So the power of 2. So that means since V1 is larger than V2, so this will be magnified, right? So this will be highly magnified. So this means object with a smaller mass is moving with a higher velocity. And this will also help you understand, suppose if you are shooting a bullet from a gun, right? The bullet is like very small in a mass, right? So that's why it moves forward with a very large speed. But the gun you are holding in your hand, the whole system is like much more heavier in your heavy. So that's why there's a recoil. But again, that recoil is not as fast as this bullet. If C would have been the correct answer, then what would happen? Rather than the person shooting a bullet, rather than the person getting hit by a bullet, the person who is shooting the bullet firing a gun would be dead. Make sense? Right? And now, to better understand another thing is like, suppose if I am throwing at you a tennis ball with a 5 meter per second speed. So you will be able to handle it and catch it, right? Yes, tennis ball. So now, okay, So now you can handle it, a tennis ball with a 5 meter per second. And since if I say mass doesn't matter, then I will throw a bowling ball at you with a 5 meter per second. Will you be able to catch it? Will you be able to handle that one?
A tennis ball versus a volleyball?
A bowling ball, bowling.
Oh, yeah, no, not at all.
Not at all, right? So why?
Because I guess, the momentum is
Yes,
so
now
much
you're
greater.
talking a language because the momentum of the bowling ball is much more higher than the momentum of the tennis ball, right? Even though they both are moving with the same velocity, the bowling ball has a lot more momentum than the tennis ball, right? Now again, it comes back down to what? Newton's first law of motion, the inertia, right? What did we talk about the inertia? So inertia is what? Nothing but a mass. Larger the mass, larger the inertia, right? Now, if the bowling ball is moving with a 5 meter per second, so it will be much more harder to stop that one because the bowling ball has a larger inertia because it wants to keep on continuing with going with the 5 meter per second speed. Compared to the tennis ball has a smaller mass, so it is smaller inertia, so you can easily stop. Make sense?
Yeah,
So now that's why this momentum comes into play. So something that you couldn't explain based on the energy model. So now here you need a momentum model. So that's why now there's another layer of physics, another model of the physics that will help you understand this more to explain the physical phenomena going on, right? Make sense? So now, so that means I can also write down my kinetic energy in terms of momentum. What is the kinetic energy? Is basically half mv squared, right? Now, if I will multiply and divide by mass, so what I'm gonna get? Mass square, velocity square divided by mass. So that means I will write down my kinetic energy as momentum squared over 2 times mass, right? So kinetic energy is proportional to the momentum squared and inversely proportional to the mass. So the larger the momentum, so if two objects have the same magnitude of momentum, then the one with a smaller mass has a kinetic energy, so more kinetic energy. So that means here this momentum is same, right? P is same in both conditions. Now if the mass is smaller, what happens to this kinetic energy? This momentum is squared divided by mass, this will be even larger. But if the mass is like really larger, my kinetic energy will be smaller. Make sense?
yeah,
Compared to the one with a smaller mass. So this is another expression I think like you guys should like write it down. This kinetic energy is equals to p squared over 2m. If momentum is constant, but if you change the mass, but like here, so that means here what are the parameters that here? Proportional to momentum squared and kinetic energy is inversely proportional to mass, right? So larger the mass, smaller the kinetic energy, smaller the mass, larger the kinetic energy. So in this expression, if we keep the momentum constant, so again, how we keep the momentum constant, we can change the variation of the mass times velocity, right? Momentum is mass times velocity. To keep the momentum constant, what you can do, if I increase my velocity by 2 meter per second, I can decrease my mass by 2 kilogram. My momentum is still the same, right? So my momentum is still the same, doesn't mean that the kinetic energy is same. Kinetic energy will be different. Make sense? Right? Okay. Oh, okay. So did I give you guys a lot of headache? That's why I need to drink water. I'm the only one talking. Okay. So now next is what? A conservation of momentum. As we did for in case of like energy, conservation of energy. For the momentum, there's a conservation of momentum. Okay. So what this momentum of conservation means? If no external force is acting on a system of particles, the total momentum P of the system is constant, which is basically what? So there is no external force, right? So meaning if there is no net force, if there is no net force acting on body, if the mass is not changing, then my velocity is always constant, right? Make sense? If no net if no net external force act on the system of particles, so that means if we are not applying a net force on the system, total momentum of the system is constant, meaning if the mass remaining constant, my velocity will also remain constant, right? Like here, if you have a two system, here we have a big SUV van and we have another sedan of mass M2, right? As they travel with this velocity, so this this sedan, this SUV, this van is traveling with the velocity v1, and the sedan is moving with the velocity v2. So now, when if this green mass is moving faster compared to this sedan, what did we see? As it moving, it hits this car, and then it will have a different velocity for the van compared to this car, right? So meaning here, so we have this car, this M1, this another car, M2. If they are moving with some velocities, right? So even though this velocity has been changed, the total momentum of the system does not change because this is the whole system before. So this two car is a one system. So meaning if you are taking a gas molecules inside a cylinder, the cylinder as a whole is a one system. But if you go inside the cylinder, there are like a lot of gas molecules vibrating in all random positions, right? They might be colliding to each other and they might be colliding to the wall of the container and everything. But the container does not move at all. Why? Because the total momentum of the system is a conserved quantity. It is like momentum before the collision and after the collision. So what happened here? So this car is moving faster compared to this fast car here, as you see from this shaded diagram. So this separation is like really, really small. But at the same time interval, this separation, this car is moving faster. But once this collides, this car moves slower and this car moves faster. So what happened here? So the velocity from this car has been transferred to this velocity, right? And the total momentum of the system is still constant before and after the collision. Does that make sense? Because these two object is as a whole is a system. If we see two different things, then yes, this is moving faster and then here is moving slower, and here it was moving faster, slower, and here it is moving faster. But if you see both together at the same in the same system, they are conserved. So like your a container of the gas molecules, the container does not move at all, no matter how the molecules are uh, moving back and forth. Make sense? Does this make sense?
Yeah, I follow it.
Okay.
So
So
are
from
they
the
both, are both vehicles then at the same inertial point of reference?
Yeah, it's the same system. They're both. So it's basically meaning like, you and like your friends in a car, inside a car, right? You move here and there, but you are still inside a car. So you two are a system inside the car. Only here, when these two cars are separate and they're moving, they are separate. But now if you put both of them in one virtual boundary, then you can see these two are is a one system. Got it? So this, if you take both into consideration, then that's a system of interest. Make sense? And from definition of impulse. Okay, so I'm talking about the impulse. Okay. So now what we said, momentum is what? Rate of change of, sorry, force is what? Rate of change of momentum. Let me go here. So here, force is what? Rate of change of momentum, right? So that means I can also write down this one as a change in momentum is force times the change in time, right? So change in momentum. So that's what it is here. So now in these conditions, this P1, the momentum of this first vehicle, so P1 is F12, so the force exerted by this one on this one times the time of impact, how long it got collided, and at what time there was a change in this exchange of this force between these two particles, right? And then change as momentum for the second car is delta P F21 times delta T, right? When they collide, there is an exchange of force, right? Between these two cars within the system. Make sense? Right? So now, according to conservation of momentum, and according to Newton's third law of motion, when they hit each other, this force F12, the force due to 1 on 2, and then force on 2 due to 1, so they are equal and opposite, according to Newton's third law of motion, right? So that means my momentum delta P1 is equals to the negative of momentum delta P2, right? Change in momentum of the first car is equal and opposite to the change in momentum of the second car. So now what is happening here? This car will give it momentum to the second car after the collision. So that's what this means. Like in Newton's third law of motion, the forces are equal and opposite. Here, the change in momentum are equal and opposite within the two object system, right? So that means change in momentum of the first one plus change in momentum of the second one is equals to 0, right? Sum of the changes of the momentum of the first car and the second car, they are equal to 0. What does that tell me? So that tells me if P1 is my initial momentum and P1 prime is my final momentum. So P1 minus P1, again, I jumped a step here. So let me write it down here. Delta P1 plus delta P2 is equal to 0, right? So now suppose delta P1 is equals to P1 minus P1 prime, where P1 is initial momentum and P1 prime is my final momentum, right? So delta P is P1 prime minus P1, right? Final minus initial, right? I can write it this way, right? P1 prime minus P1. So similarly, delta P2 will be P2 prime minus P2. Okay. So now if I add this thing up, P1 prime minus P1 plus P2 prime minus P2 equals 0. Now if I rearrange them. So P1 prime plus P2 prime equals to P1 plus P2. Or I can say P1 plus P2 is equals to P1 prime plus P2 prime. So now this is what? Before collision. And this is what? After collision. Right? So the total momentum of the two cars before collision and total momentum after the collision, they are equal. And this is called conservation of momentum. Make sense? Make sense? So this is a constant quantity. So that means total momentum before the collision and total momentum after the collision is a constant quantity. So now, so momentum is simply defined as m1 v1 plus m2 v2. So this is initial momentum before the collision, and m1 v1 prime plus m2 v2 prime is the momentum after the collision. So this is one of the expression for the momentum conservation. m1 v1 plus m2 v2 is equals to m1 v1 prime plus m2 v2 prime. Again, here we are considering the mass is constant, relatively constant. Okay, mass is not changing, only the velocity is changing in these conditions. Okay. Okay, I think like we are. Okay. I think like I'll stop here today and we'll continue remaining on Thursday. Does that make sense? Because I don't want to fry your brain with like too many new things. Okay. Okay. So do you have any questions before we leave?
Could you post these notes?
Oh yeah, sure. I'll post this one. I'll do it right now before I leave. And also like
Thank you.
another thing, this book, right? So if you go to the Blackboard, so like I'll show you what I mean here. If you go to Blackboard, let me pull this thing off. If you go to Blackboard, and then there's a syllabus posted here, right? There's a syllabus, and if you click the syllabus, and you will open up this one. All the informations are here, and I talked about this in the first day of the class, and all your homeworks, like how they are scheduled. So it's all here. So your homework 3 will be due on Thursday, by Thursday. So where you have of like work and energy only, the homework 3, and these are the chapter and sections that we will be covering in a class. So right now we are in chapter 8. We just covered momentum and we just covered like conservation of momentum, right? And we haven't done the problem, but we will do that one after that one. And these are the sections 8.3, 8.4, 8.5, and 8.6. So these are the sections that we'll be covering: inelastic, elastic collision, impulse, and center of mass, that we will be covering in this chapter. And we don't need to do anything about like a two-dimensional. It's good to know if you learn yourself, that's really good. But for this course, we don't need to do that. Okay, right? So these are the things that we're gonna do. Other than that, and then also like if you read ahead of a time, so it will prepare you for the class, and then you can also ask question and answer, and then it can be interactive. Okay. And now we will be covering this rotational dynamics and the dynamics of rotation. And then November 12 to 14. So there is like another exam. Okay. Anything? Do you have any other questions? Yes, Mariam, we can talk about it. So, okay. Anyone? Any questions? If not, then you're good to go.
Thank you.
Good night.
Thank you.
Mhm.
Real quick, I just realized that I didn't sign into the attendance. I guess I missed it when you did the code earlier. Sorry.
Okay, so just let's see here. How your mic all of a sudden started working?
Mine has always
Mary?
worked. Oh,
Really?
I get nervous talking in front of people.
And then there's no interaction with the typing as well. There's no with it typing,
Oh, I usually
right?
don't know the answers.
So that's not good.
Yeah. It
And
usually
how do I
takes
know
me.
you were in a class? And how do I know you were in a class?
Oh, I mean, I
Your
have
camera
on
is
my
off.
phone.
Yeah. Okay. Yeah, I know. So that's not the learning works. Sorry, I'm putting you in a spot. That's not the way learning
No.
works. And it's not for me. It's not for me. It's for you guys, right? If you guys like ask questions and do things, and it will be good for you.
Yeah.
I
I
cannot.
think I take my notes and then afterwards I try to do it like more learning by myself. I don't know.
Okay, so one thing, what will be better? So like after my lecture, rather than studying after my lecture, just go for like 1 hour, 2 hour to the chapter material that we're gonna cover, right? In the syllabus, I mentioned what are the topics, right? And if you do that one, then there are like so many questions that comes to you in your mind because you might not understand each and everything, or you might find it so interesting, so you understand, oh, it makes sense, right? And then when you come to the class, then you will be able to participate very efficiently. And then you will not be what do you call it? What did you say? You feel like what?
Oh, I just don't
Uh,
really like talking in front of people. I don't
yeah.
know.
So
Especially on Zoom. It's not my
what?
favorite.
So okay, so then you should do for like face-to-face class.
Yeah, I wasn't available. Like this was kind of so I'm applying to OT school and only one of the
Uh-huh.
schools that I'm because not every school requires physics, but one of them that I'm applying to does. So I kind of last minute decided to take physics and it's
Uh-huh.
been a while since I've done like
So
a math class,
so
so it's
you-
yeah, I
you're
kind of
saying like
struggle.
OT you are doing, right? You're doing like
Yeah.
OT class, right? Occupational therapist, right? So that means you have to talk to people a lot, right?
Yeah. But it's in person. I agree. I should have done it in person, but
Yeah.
it was last
No, no,
minute.
no. Even the occupational therapist, right? So like some people you can also help them remotely by the Zoom, right? So do this, do that, right? And all those
Mhm.
things, right? This is also one kind of a skills. And take this as an opportunity, right? So come out of your comfort zone.
I'll
Come out
try.
of it.
Yeah.
So that would really help. Right? And I can tell you from my experience, like, I was a kind of a guy who doesn't used to talk to anyone in my class itself. In my grade 10, while I was in a grade 10, I still remember we were 7 students
Mhm.
in a class, and I don't used to talk. And I did not know their names.
Yeah.
In my grade 11, so I used to go for private tutoring, and there were like 6 or 7 boys, right, in a class. For one whole year, I did not knew any of their names.
Oh wow.
I did not knew for one whole year. So, and we were around the table, not like in a different benches or different chair. So like really sitting next to each other. And I didn't know their names for one whole year. And second year, when I again did the private tutoring, same people and some extra people were there. And then they were talking and then introducing to each other. And then like I was in like awkward, like now I have no escape. So now they are in the second year also in the same tutoring, like that kind of thing, right? And then I was like so much behind, even though I was like academically good, but like I was so much behind because I was not able to put my thought in front of them. I was not
Yeah.
able to discuss anything. So whatever the problem I had with me. Whatever the knowledge I had with me. Whatever the confusion I had with me. I didn't share to anyone, so that confusion never got clear. And this anxiety, the social anxiety, it was always there, right? So come out. So this is the time for you guys, the opportunity. So like, because from my experience, I'm telling it from you, my experience, because you don't want to be 40 and learning this, right?
Right. Yeah, no, I agree. Physics is not one of my strong suits.
Right.
And so I feel
So
like if I do
that's
answer,
why
it'd be wrong. So it's,
that's why you are taking the course. That's why
yeah,
you are taking the course, right? If you have none already, then what's the purpose of taking the course? If you
yeah,
know already everything, then why you're taking this course, right? Right.
right, yeah,
So that's why like I'm trying to put, like a more depth, more understanding, more conceptual, right? So I get mad if no one responds. I don't get mad if someone gives a wrong answer, right?
yeah,
And then I just want to see, like, so like today, so like there were like so many problems. Many of you got like a correct answer, but I was trying to see what was the process. But the process was not the correct process. It was a fluke that it got a correct answer, right? So that's
mhm,
what I was trying to learn. But did I say anything to them? No, 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 you are wrong. How did you do that? Can you? No, right? It's a learning process. So it doesn't matter. So that's what I want to see. Where do you make a mistake? And how do I correct that one? Right? How can I help you uh, see the clear picture, right? So because this physics is all word problem, it's all muddy water, right? And how to make it clear,
Um,
right?
one thing I was wondering is, would you be able to post an equation sheet onto the Blackboard? Because I think for me, a lot of the times it's like there's so many equations like in like my notes or in PowerPoints or whatever that I'm kind of like I
Mhm.
struggle to be like, okay, where like I write down like all the like, okay, this is the mass, this is the velocity or whatever. But then I'm kind of like, oh God, which equation? So would
Okay,
that be
so like
possible?
for the midterm one, so there's a equation sheet already I have published, right? For the midterm one, so there's the
Yes.
equation sheet, right?
Yeah.
So I can put down the equations, right? Based on the chapters, that's fine. So that if that helps you, that's okay. I'll do that. Okay.
Okay.
And
Thank
but at the same time, do your part as well as I am asking you to do. Interact.
Yeah. I'll try
Okay.
to be better at it. I just,
Okay.
it'll probably be the
So
wrong
yeah.
answer. Sorry.
I really get mad, like, when I ask questions and then, and you can hear me like with my voice and my tone, right? So I'm
Yeah.
asking questions and no one answers, and asking twice and I thrice, and like, and I get really, really, really mad because I'm not mad because you don't get it. I'm mad because you don't participate.
Yeah. I think my issue is I just get embarrassed that I don't know it. And so I'm kind of just
No,
like,
there's nothing to be
which
embarrassed, right?
it's,
There's
I
nothing
don't
to
know,
be embarrassed,
it's silly, but
right?
it's just, yeah.
So you don't have to be perfect. It's like even I don't have to. Even I'm not perfect. Like, sometimes I might have to say, oh, "Okay, that's a good question. I haven't thought about it, so I have to check. I have to look at it, right?" And then I
Yeah.
go look at it, and then next time, right? So that's fine. That's fine. No one needs to know everything, right?
Right.
So only thing is like you should know how to find for the answer, how to look for the answer, right? So yeah, that's the thing, right? So because when you go into your job, right, your OT, like, so you might find a different kind of patients coming to you, and it's like, oh, you are like occupational therapist and you don't know. No, it's not needed. But you know how to dig into that particular. You know what are the resources available for you for that particular field, and you can find the answer much more easier, much more quicker, and much more better answer, right?
Right.
So there's nothing to be embarrassed. So come out of that
Yeah.
comfort zone of like being like not embarrassed.
I'll try. Okay.
Yeah.
All right.
So
Well,
okay,
thank you.
for today, for today, I will uh, give you a credit for the class, but
Yeah.
again,
So I don't know how I missed that
not.
either because I had the chat open, but it didn't, I guess it didn't register for me to do it today.
Uh-huh.
Okay.
Okay.
Thank you. Have a good
Okay.
night.
No, you too.
Bye.
Hi, Mariam. Sorry, I I was taking a little bit time. And I cannot hear you because you are mute. Or I cannot hear you because you are not in front of the computer, maybe.